Today you'll be learning lesson 7.6 on exponential functions. Our goals for today is we're going to be sketching exponential functions, which means graphing, okay, and identifying data that displays exponential functions, which means we're going to be deciding if a set of data, a table, represents exponential data or linear data. Okay? So what we need to know in order to do this is some review of linear functions. Okay? If we remember back to when we were working with linear functions, we need to remember that linear functions have a constant rate of change. Okay. Which means every single time we are adding or subtracting that same thing to x, and every single time we are adding or subtracting that same thing to y. Okay? So with exponential functions, that doesn't happen anymore. Okay? If you think about exponents and what we've been working on, the more you increase that exponent, it gets quite a bit bigger. Like 2 to the second power is 4, but 2 to the third power is 8. Okay? It's not just adding 2, it's doubling what that was before. Okay? So with exponential functions, since they have to increase faster, what happens is we look for a constant difference in our x terms, right? Which is the same thing that was happening to x before, okay? But it's called a constant difference. Okay, so the x is going to look just like it did when it was linear, right? Which means we're either adding or subtracting that x term, okay? But now our y-coordinates are no longer addition or subtraction. Okay? These are said to have a constant ratio. Okay, and what you'll hear me refer to that a lot as is a constant multiple. Okay? Because what's happening to all your y-coordinates is they're being multiplied by something every single time. They're no longer just adding or subtracting. So when you look for that pattern, you're going to have to find out that it's multiplication. Okay, so let's look at our first example. Okay, when I look at my x's, from 0 to 1 is still plus 1. From 1 to 2 is plus 1. From 2 to 3 is plus 1. And from 3 to 4 is plus 1. Okay, no change. But when I look down here, from negative 1 to negative 3 is minus 2. But now when I go from negative 2 to negative 9, it's no longer a minus 2, so that pattern doesn't work, right? So we need to figure out what is happening right there. I'm drawing a question mark here. Okay, so we know that's no longer an addition or subtraction relationship. So what we look for is if there's a constant multiple, that constant ratio. So I know to get from negative 1 to negative 3, I can multiply that negative 1 by 3. Okay? And if I'm at negative 3 and I need to get to negative 9, I can multiply it by 3, because negative 3 times 3 is negative 9. If I keep checking that, negative 9 times 3 is negative 27. And negative 27 times 3 is negative 81. Okay, now since this is multiplication, okay, since we're multiplying on those y-coordinates, we have an exponential function. Okay? And that's because our x has a constant difference, of 1, but y has a constant multiple or constant ratio of 3. I don't care which word you use ratio or multiple. Okay. Making it that exponential function. Okay. So we look at the second table. Okay. You notice they're kind of closely related. From 0 to 1 is plus 1. From 1 to 2 is plus 1. From 2 to 3 is again plus 1. And from 3 to 4 is plus 1. Okay. Now let's look at the y's, but if you look at the y's, there's actually a mistake in there. So let's change these last two parts of our table to a -7 instead of a -8, and then a -9 instead of a -11. That was our mistake. Okay? So now when I look at those, from -1 to -2, or to -3, I have to subtract 2. From -3 to -5, I again subtract 2. -5 to -7, I subtract 2. And -7 to -9, I subtract 2. Giving us that constant rate of change, which means we have a linear function. And this one's easier to explain because it's review. It's a linear function because it has a constant rate of change. Okay, so that's the difference between a linear function and an exponential function. Okay. So exponential functions. In a linear function, we have y equals mx. Okay, we have y equals mx plus b. We have ax plus by equals c. And we had that y minus y1 equals m times x, the quantity of x minus x1. Okay, exponential functions, we only have one form. Okay, and what they look like is y equals a times b to the x power, where our a cannot be 0. Okay? A cannot be 0. Our b has to be greater than 0. Okay? And it can also not be 1. Okay? So what you see when you look at these is these functions have no addition or subtraction. They're all multiplication. Okay? They're just multiplication. So when we look at these bottom ones, we have some examples. 2 to the x power. And again, that x always has to be your exponent. So when we evaluate these, you're going to see that x becomes where we substitute. Okay? The second one, y equals 5 times 3 to the x power. And the third one, 1/3 to the x power. All of those are examples of exponential functions. So to graph these, okay, just like when we started graphing linear functions, we're going to graph these by making input-output tables. Okay, where we have that x column, that middle column for our work, and our y column. Okay, so we're going to graph y equals 2 to the x power first. So let's make our table. We need x, we need our middle column for our work, which is 2 to the x power, and we need our outputs, our y's. Right? And just like before, when we start graphing these, we're going to start with -2, -1, 0, 1, and 2. Okay? So when I substitute, right, 2 to the -2 power. Remember, a negative exponent means we flip that around, which means I have 1/2 to the second power, which is 1/4. When I do the second one, a -1, 2 to the -1st power, means I flip it over and I get 1/2 to the first power, which is 1/2. 2 to the 0 power, we should know again doesn't take any work, so my answer is 1. 2 to the first power should be a pretty simple one. 2 times nothing is just 2. Okay? And 2 to the second power means 2 times 2, which is 4. Okay? So when you graph this at -2, I'm way close to that x-axis. I'm way down at 1/4. Okay? When I move to -1, I'm up to 1/2. Not a very big jump. Okay? But at 0, I'm up to 1. And at 2, or at 1, I'm up to 2. And at 4, or 2, I'm up at 4. Okay, so you should end up seeing that this curves, switch my colors here, that this curves upwards. It starts really, really close to that line, and it curves upwards. Okay, that's an exponential function. Okay, they're either going to curve up or they're going to curve down. Okay? So if you think about that, when you plug in 3, hey, if you got 2 to the 3rd power at 3, we should already be up at 8. Okay, so if you look at those dots, they start really close together down here, right? They only went up 1/4 of a box, okay? But when we get over here, they're moving up 2 boxes at a time. It's not constant anymore, okay? So let's look at the second one, okay? When I have y equals -2 to the x power, right? So now I'm going to use my same numbers. X column, I need my -2 to the x power, and I need my y. -2, -1, 0, 1, and 2. So -2 to the -2nd power, right? Again, that negative exponent means we flip it over. But this time, if you notice, there's no parentheses, so that negative is going to stay there. So I have a -1 over 2 to the 2nd power, which gives me a -1/4. Okay, so -2 to the -1st power. Again, there's no parentheses around there, so that negative stays. So I have -1 over 2 to the 1st power, which is -1/2. Okay, -2 to the 0 power. Okay, again, that negative is not in parentheses, so our negative stays. So it's actually a -1. -2 to the 1st power, it's going to stay -2. Okay. And -2 to the 2nd power is really still a negative because it's not in parentheses. So we have a negative and then a 2 times 2 to get -4. So if you notice, the only difference between these functions is the first one, every single answer was positive. And the second one, every single answer is negative. These two are actually reflections of each other, right? So when I graph this one at -2, this time I'm below that x-axis at 1/4, -1/4. -1, I'm at -1/2. At 0, I'm at -1. At -1, I'm at -2. Right? And at 2, I'm at -4. So this time, rather than pointing up, our curve is pointing down. And that's how we graph exponential functions. Right? Remember, if there's not parentheses, that negative is not to that power. Okay, so let's have you try this one. Right? If you want to pause the video and try this one on your own, that would be a great idea. Right? But I am going to work through it. Okay? So, to graph this one, again, I need to make my table. X, our work column. This time, if you notice, that whole entire fraction is to our x power, and our y. Using -2, -1, 0, 1, and 2. Okay. So if I have 1/3 to the -2 power, the first thing I need to think about is I need to flip that around, right? So it becomes 3/1 inside, and then I have to distribute that 2 to both of those, okay? Which really, having a 1 squared on the bottom is still 1, right? So I really have 3 squared, which is 9. Again, if you know how to type these into your calculator, you can do that too. Okay, so 1/3 to the -1 power means I need to flip that fraction over. So I have 3/1 all to the 1st power, which if I distribute that, okay, is still just 3. Okay, 1/3 to the 0 power. Remember, anything to the 0 power is 1. And 1/3 to the 1st power really just means 1/3. And then 1/3 to the 2nd power which is really 1 squared over 3 squared, is 1/9. Okay, so I have my points to graph. Okay, so if I'm at -2, it says I'm way up here at 9. At -1, I'm down here at 3. Okay. At 0, I'm at 1. At 1, I'm at 1/3, which is below a half. And at 2, I'm at 1/9, which is really, really close to the x-axis, but not there. So again, you notice those dots are not equally spaced, right? Making it that exponential function. So I'm going to start that top dot and curve around through. And if you notice when I'm drawing my graphs, your curve should never go through the x-axis, right? You do not want this to pass that axis right now, right? Because you think about it, you're never going to get an answer of 0. Your numbers are just going to keep getting smaller and smaller. So evaluating an exponential function, right? Remember, to evaluate really just means to solve. So if we're evaluating an exponential function, what we're doing is substituting into that function and solving. But today, you need to make sure you read your questions carefully. Okay? This one says, suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles every week. Okay? The function f of x equals 30 times 2 to the x power gives the population after x weeks. How many beetles will be in there after 56 days? Okay, the problem with this one is that all the information for the equation is in weeks, right? But the number they gave me is in days. So my first step is to convert that 56 days into weeks. And the way we do that, we know there's 7 days in 1 week, so we take that 56 divided by 7 to get 8 weeks. And now I'm ready to evaluate my function by substitution. So we have f of x, and if you want to sub an 8 right there, remember that's what that is saying, f of 8, finding the value after 8 weeks, equals 30 times 2 to the 8th power. So to evaluate this, we follow the order of operations, and the first thing we do is our exponents, okay? 2 to the 8th power, if you don't know that, type it into your calculator. You get 30 times 256, which when you multiply out is 7,680, and it's a word problem, so we need to label it beetles. Evaluating a function, just like evaluating an equation. We substitute and we solve. So try this next one again. If you would like to pause the video, now would be a great time. If you want to try this one on your own before you see me work through it, would be a good idea. Alright, so this one says an initial population of 20 rabbits triples every half year. Right? The function f of x equals 20 times 3 to the x power gives the population after x half-year periods. How many functions, or how many rabbits, will there be after 3 years? Right? We have a problem again because our function is given to us in half years, so we need to think how many years, or how many 3 years equals how many half years. Okay, well in each year there's 2 half years, so I take that 3 times 2, and we know that there's 6 half years in 3 full years. So to evaluate my function, I'm going to plug in that 6 for x, so f of 6 equals 20 times 3 to the 6th power. Order of operations again, we got to do that 3 to the 6th power first, right? Which gets me 20 times 729 to get a final answer of 14,580 rabbits. Again, still evaluating, substitute and solve, and if it's a word problem, make sure you label. Okay. So really quick review, okay? Does the following table represent exponential behavior? Why or why not? And I realize those numbers are really hard to see in the video, okay? But hopefully you have your notes out in front of you and you're following along with us, okay? So let's first look at our x's, okay? They're going up by 6 each time, which no matter which type we're talking about is how we want. Our x is always just an addition problem, okay? And if we look at our y's, well, 64 to 32, we know that we subtract 32. Well, from 32 to 16, that doesn't work anymore. So now I need to think about that multiplication, right? So if I want to think about that, we know that 32 is half of 64. And if you guys think those bigger numbers at the front of your table are harder to work with, then it's perfectly fine to start by looking at the numbers in the back. Okay, so if we have to be multiplying, what do I do to 4 to get to 2? Well, 4 divided by 2 is 2, which is really multiplying by 1/2. Okay, from 8 to 4 is again 1/2. From 16 to 8 is 1/2. From 32 to 16 is 1/2. From 64 to 32 is 1/2. Okay, so just from looking at that table, we know that this is exponential behavior. So does it represent exponential behavior? Yes. And to explain, x has a constant difference. But y has a constant ratio. And again, if you want to call it a constant multiple, that is perfectly fine because you're multiplying each time. So I'm 100% okay with that. Okay? And if you were to graph that, you would again notice your graph is that curve. Okay? Starts up nice and high, curves down nice and low to that x-axis. Whereas in this one, okay, my x's are going up by 3, which is always, again, what we need. Our x has to have that constant difference. But our y's, from 16 to 20, I have no idea what I can multiply to get there, okay? So I'm first going to, before I figure out anything multiplication, if you don't have a clue, check for addition or subtraction. Because 16 plus 4 is 20. 20 plus 4 is 24. 24 plus 4 is 28. 28 plus 4 is 32. And 32 plus 4 is 36. Okay? Which gives me that constant ratio, or constant rate of change, sorry. So this one we know is not exponential behavior because it has a constant rate of change. Which makes it linear. Okay. And that's lesson 7.6 on exponential functions.